Okay, in this video we're going to discuss high-pass filters. Once again, these will be first-order high-pass filters. They will be passive filters, which means they're either an RL or RC, no op-amps, no transistors, no active elements. They will also be first-order, meaning there's a single energy storage element, either an L or a C in the circuit. So the first circuit to look at is the series RC. The series RC high pass filter is different from the series RC low pass filter because in the high pass filter we take the voltage output across the resistor. That is because the impedance of the capacitor at very low frequency appears to be infinite. So remember, at DC a capacitor is open. So we have this open circuit then under DC conditions and for very low frequency conditions. So in that case, no voltage will appear across the resistor because it will all appear across the open circuit. As the frequency increases, 1 over j omega c becomes a smaller number until ultimately, when the frequency is high enough, the capacitor looks like a short, which means all of the voltage, as in shown in figure C here, all of the voltage is going to appear across the resistor. So we have a case where the output voltage is equal to the input voltage at high frequency and the output voltage is equal to 0 at low frequency, which means we have a high pass filter. So we'll skip over some of this because it's just what I just said. And here's what the frequency response plot would look like then for the RC circuit without doing any math yet. Basically, you would start off in the stop band or the cutoff region, and slowly the output voltage will increase. Right at cutoff, it will be 0.707 output over input, and then as you increase the frequency above cutoff, you ultimately will approach a ratio of 1 for the transfer function. Likewise, the phase, it changes nonlinearly as well because this is not an ideal filter. So if you do the same kind of analysis that we did both in class as well as in the first lecture on low pass filters, you'll see that you basically come up with a transfer function. H of s is s over 1 plus, or s over s plus 1 over RC. We now follow our standard procedure of substituting j omega for s, and we get this expression shown right here for h of j omega. And now, because this is complex, remember that h can be separated into two different equations, one for the magnitude and one for the phase. So we do that in the next step, where we find the magnitude by finding the magnitude of the numerator and the magnitude of the denominator separately. And then we find the phase. So in this case, the numerator is j omega, which has a phase angle of 90 degrees. The denominator will have a phase angle of the inverse tangent of omega over 1 over RC, which turns out to be omega RC. And because that's in the denominator and this is an angle, a phase angle, we can then pull that up. So we get 90 degrees minus the inverse tangent of omega RC for the phase. Like previously in examples, you can plug in different actual numerical values for omega. If you know the values of R and C, you can actually get the magnitude and the phase of the transfer function at any value of omega. So if you want the cutoff frequency, you set the magnitude of H equal to 1 over the square root of 2, solve for omega C, and you find that the cutoff is 1 over RC. Exactly the same as what we saw when we did the low pass filter. All right, so we can also design a series RL. Remember that as omega is small, approaching DC, an inductor looks like a short. As omega approaches infinity, an inductor looks like an open. So for the series RL high pass filter, we'll take the output voltage across the inductor. You can write the transfer function for that using a voltage divider, and you end up with this expression for H of S being S over S plus R over L. Once again, following our procedure to substitute j omega for s, you can do that and you get the following expression for h of j omega. And then you can find the magnitude for that in terms of omega and r over L. You can find the cutoff frequency by setting the magnitude equal to 1 over the square root of 2, and you determine that the cutoff frequency is r over L. And then finally, if you have a desired frequency that you would like to filter, in this particular example, we'll come back up and read the actual example problem where we're asked to choose values for R and L that will yield a high-pass filter with a cutoff frequency of 15 kilohertz. So coming down here to our expression, and for solving for L, we take R over omega C, and when we do that, we can choose a 500 ohm value for the resistor R. We then plug in our 15,000 hertz, and we have to multiply that by 2 pi to get it in radians per second. Solving for L, we get 5.31 millihenries. Now, I do want to make a couple of comments about the materials and the way they're presented in the book. First of all, typically in an actual design problem, you are choosing the value for L because you have a little less leeway with choosing an inductor value unless you're actually winding it by hand. So often you will find the L's that are available, and then you'll solve for R because it's a little easier to find a resistor of various values. So in that regard, this particular design problem example is maybe not the greatest, but it's not, terrible. So anyway, that's how you would work a design problem for a series passive RL high pass filter. Now, filters can be loaded. So typically, when we have an RL filter, that doesn't just exist independently in the universe. We often are applying some signal to some load. So in the real world, you would have your RL filter, but then you would have a load here that's shown by this load resistor that's typically placed in parallel with the output of the inductor. Now, whether this is a load where you're actually delivering a signal or some power to something, or maybe it's a load because you're trying to make a measurement, it varies. But typically, you don't have a true open circuit. You actually have some non-infinite value of a load resistor that's hooked to your filter. So the point of this example is to illustrate in the real world what the effect of adding this load resistor is. So if we just, in this particular case, work through this example, basically this impedance becomes the parallel combination of L and RL, and then we can do a voltage divider between R and that equivalent impedance. So that's what's done here. This top term is the parallel combination of that load resistor and the inductor. The bottom term is the sum of the two. So this is the voltage divider relationship. And then if you divide through by input voltage, you get the transfer function. So this is what the transfer function looks like. Doing some algebra between this expression and this expression, we find that we get the following expression here, which is some number times S over S plus another number. So first thing is, we always know that the behavior of the circuit is dominated by what's in the denominator as far as the location of the cutoff frequency. So as I mentioned in lecture 1, because sometimes we have a gain or a product in the numerator that is not necessarily something that we would typically have, we always search for the cutoff frequency as being the pole of the denominator. So in that case, this is our denominator pole. Now, you may kind of think about this. What would happen if we didn't have the load resistor? If we didn't have the load resistor, this value RL goes to infinity because it's an open circuit. So this term, RL over R plus RL, would approximately be equal to 1, in which case our omega C, our cutoff, would just be R over L for the actual filter elements, and our numerator would just be S. But because we have that load resistor on there, we now have two things that have happened. First of all, in the numerator, we have this constant term K that's equal to RL over R plus RL. And the closer the load resistor gets to the resistor in the filter, the more this K impacts the total magnitude that you can have. So normally, if we did not have a load, our gain at low frequency, or our value of H at low frequency, would be 1. If we have a load, that now becomes a voltage divider ratio, or a divider ratio, between the load resistor and the sum of the load resistor and the filter resistor. So K, in this case, for a passive filter, will always be less than 1, and we can refer to that as the gain. Also notice that this ratio shifts the cutoff frequency. So our cutoff frequency for the loaded filter is no longer R over L. It's now this K times R over L. So the cutoff frequency has shifted, and because this term is always less than 1, the cutoff frequency will shift to the left, so it will become a lower frequency. So if the goal is to have your cutoff frequency set at some value for your high pass filter, the effect of loading the filter lowers that cutoff frequency, meaning you pass lower frequencies than perhaps what you intended to pass. So it's important, if you're doing a design and you know what your load's going to be, it's important, if you have a real specific requirement on your cutoff frequency, to take that into consideration when you're going to load your filter. This is why sometimes people will build something in the lab that they think will have a certain performance. Then they hook it to a load and never took into account that you're going to have a loaded filter, and that's going to then impact your cutoff frequency and give you a different plot than you would expect. So K and omega C then are both affected by the loaded filter. We can come and actually do the mathematics, and we can look here at what happens for a specific filter when you have both a loaded and an unloaded case. So first of all, you note that in this case, let's see what we're doing. We have an unloaded filter. The passband magnitude is 1. The cutoff frequency is 15 kilohertz. When we load it, the maximum gain that we get in the passband is 1/2. That's when when the load is equal to the impedance of the filter, to the resistance in the filter. Our gain would be 1/2, and our cutoff frequency would be 7.5. So if you look here, here's our unloaded filter. Here's our cutoff frequency. We're approaching a gain of 1. As soon as we put a load on that filter, notice that our cutoff frequency has shifted back, and our total gain is here at 0.5. So it's going to change both your frequency response characteristics as well as the total magnitude that it will output in the passband. So that's pretty much what I want to say here, other than to skip to this general transfer function for a high pass filter. So the general transfer function has the appearance S over S plus omega C. Note that this is not a loaded filter because we don't have this value K in the numerator. So this is for just a first order high pass filter. The difference in the transfer function in the high pass filter and the low pass filter is in the low pass filter we had an omega C in the numerator and no S. In the high pass filter we have an S in the numerator and no omega C. And either one of those filters, either high pass or low pass, can be loaded, giving you a change both in your cutoff frequency as well as in the overall gain of the filter. So here shown together are the RC and the RL high pass first order passive filters, and you can see what the transfer function looks like, where in the case of the RC you're taking the output across the resistor. In the case of the RL, you're taking the output across the inductor. The cutoff frequency is 1 over RC for the capacitive circuit, and it's R over L for the resistive circuit. So just like the low pass filter in the high pass filter, we can get some generalities. So there is an example in the textbook materials. Basically, if you have a copy of the textbook, of electronic version of the textbook, you can go and watch this example where they illustrate how to find the transfer function for a passive filter with a load. So that concludes the two types of passive filters for first order. I want to skip over this stuff and get to the chapter summary so that we can look at this together. Look at these together. All right, so here we go. So where we are is we have talked about definitions, low pass filters, and high pass filters. So recall the definition of the passband. This contains the frequencies of the signal that are passed on to the output. The stop band is the frequencies of the signals that are attenuated. The cutoff frequency is what separates the stop band from the passband, and it's defined as the point where the transfer function has a magnitude of 1 over the square root of whatever its maximum was. A low pass filter passes frequencies below the cutoff and attenuates frequencies above the cutoff, and its general transfer function looks like this. A high pass filter passes frequencies above the cutoff and attenuates frequencies below the cutoff, and has a transfer function that looks like the one shown here at the bottom of the page. So that's pretty much a summary. So just to add some additional definitions, the filters that we've looked at, RL and RC, both high and low pass, are first order, meaning a couple of things. It means there is a single cutoff frequency. It means there is a polynomial raised to the power 1 in the denominator. So that is first order. They are also passive, which means we have only resistor and inductor or capacitor. And they only have one energy storage element. So the single energy storage element, the fact that we have S raised to the power 1, the fact that we have a single cutoff frequency are all characteristics of a first order filter. The fact that it is only resistors and either inductors or capacitors is characteristic of a passive filter. Now, it is possible to have a single cutoff frequency in a second order filter, which we will talk about in chapter 15. But for passive filters, right now what we're talking about is the simple first order low pass filter and the simple first order high pass filter.